We know that the harmonic series 1 plus 1/2 plus 1/3 plus 1/4 and so on and so forth is divergent, but its alternating counterpart 1 minus 1/2 plus 1/3 minus 1/4 and so on converges. So we can see that we get different behavior depending on whether or not the terms of a series are always positive or occasionally negative. We're going to examine that a little further with the ideas of conditional and absolute convergence. Let's start with some definitions. A series converges absolutely if the same series with the absolute value of each term taken also converges. A series converges conditionally if that series converges, but that series with only positive terms diverges. We've already seen examples of this difference. The alternating series, the sum from n equals 1 to infinity of -1 to the n plus 1 times 1 over n, the alternating harmonic series, converges. On the other hand, the series, the sum from n equals 1 to infinity of 1 over n, the harmonic series, diverges. This tells us then that the alternating harmonic series, the one you see on the left here, converges conditionally because its counterpart with only positive terms fails to converge. It turns out that if a series converges absolutely, in other words, if the series with only positive terms converges, then the same series with both positive and negative terms also converges. However, if a series that includes negative terms diverges, then that same series, including only the absolute value of those terms, in other words, the same series with all positive terms, is also going to diverge. Let's take a look at these ideas in action. Let's consider the sum from n equals 1 to infinity of -1 to the n plus 1 times 1 over n squared. If we were to take the absolute value of each term in that series, we would then get the sum from n equals 1 to infinity of 1 over n squared. That is a series that we know converges using the p-series test with p equals 2. Because that series converges, that tells us that our original series converges absolutely. But we know that any series that converges absolutely also converges. Let's contrast that to the sum from n equals 1 to infinity of -1 to the n plus 1 times 1 over the square root of n. In this case, if we take the absolute value of each term, we end up with the sum from n equals 1 to infinity of 1 over the square root of n. We can again apply the p-series test, but this time p is equal to 1/2, which means our series diverges. That means we're going to have to do a little bit more work to discover whether or not our original series converges at all. Let's apply our alternating series test. In order to determine if this thing converges, we need first to know that its terms are non-increasing. We know that n is less than n plus 1. That tells us that the square root of n is less than the square root of n plus 1, which then in turn tells us that 1 over the square root of n is in fact greater than 1 over the square root of n plus 1. That tells us that our terms are decreasing, which of course is even stronger than being non-increasing. So we have checked off the first condition in our alternate series test. Next, we have to look at the limit as n goes to infinity of the a sub n's, which is 1 over the square root of n. But of course, as n grows towards infinity, the square root of n also grows unboundedly, which means this limit is exactly equal to 0. We have satisfied both conditions of the alternating series test, which means that this series converges. However, because its all positive counterpart, the sum from n equals 1 to infinity of 1 over the square root of n, diverges, we're going to classify this convergence as conditional. So we know the sum from n equals 1 to infinity of -1 to the n plus 1 times 1 over the square root of n converges conditionally. We'll summarize this by saying that if we have a series that involves some negative terms, we're going to consider its convergence in comparison to the same series with all positive terms. If the series with all positive terms converges, then we say our original series converges absolutely. If instead the series with all positive terms diverges, but the series containing some negative terms converges, then we call that convergence conditional. We also know that if a series converges absolutely, then it must converge.